Welcome to the session on the binomial expansion, expanding 1 plus x to the power n. The objectives for this session are to expand 1 plus x to the power n for negative and rational values of n, and also specify the range of values of x for which this expansion is valid. The binomial expansion for a natural number n is a plus b all raised to the power n, as shown on your screen. Here, n choose r is equal to n factorial all over r factorial times n minus r factorial, where n factorial equals n times n minus 1 times all the way down to times 3 times 2 times 1, and 0 factorial is equal to 1. There are n plus 1 terms, and therefore the formula produces a finite number of terms. From this we can deduce that 1 plus x raised to the power n is equal to the expression you can see on your screen. Here, mod x is less than 1 and n is in the real numbers. When n is not a natural number, none of the factors in the expression n times n minus 1 times all the way down to n minus r plus 1 are equal to 0. This version of the binomial expansion produces an infinite number of terms. The expansion is valid for any n in the real numbers, but only when mod x is less than 1. We are now going to look at the procedure for writing the expansion of 1 plus x raised to the power n. First, write the expression in index form. Next, replace n and x by the relevant value or variable. If n is not a positive integer, then no coefficient will be equal to 0, and this will give an infinite expansion. And finally, in the expansion of 1 plus bx raised to the power n, where n is negative or a fraction, the expansion is valid for mod bx less than 1. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We're going to begin by writing the expression in index form. So 1 over 1 plus x is written in the form 1 plus x all raised to the power minus 1. Now let's consider the expansion itself. We're going to replace n by minus 1, as shown here, 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 and here. Notice that x does not need to be replaced, because in the general form we have 1 plus x, and in our example we also have 1 plus x. So we're going to leave x as it is. Now, if n is not a positive integer, no coefficient will be equal to 0, thus giving an infinite expansion. And this is why we have the plus ... at the end, because n is equal to minus 1, which is clearly not a positive integer. Our expression can now be tidied up. And tidying up some more. And therefore we have the first 5 terms in the binomial expansion of 1 over 1 plus x. Finally, we need to consider where this is valid. The expression is going to be valid when, in the general form, for 1 plus bx, mod bx is less than 1. So for our series to be convergent, we need to have mod x less than 1, as highlighted. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are required to write down the first 4 terms in the binomial expansion of 1 minus x, all raised to the power 2/3. The first step we need to take is write the expression in index form. As 1 minus x raised to the power 2/3 is already in index form, we don't need to make any changes. For the next step, we need to consider the values of n and x. We are going to replace n by 2/3, since n equals 2/3. So we replace it here, here, and here. And we're going to replace x by minus x. So here we already have minus x. We're going to replace x by minus x here, here, and here. Also remember that if n is not a positive integer, then no coefficient will be equal to 0. So therefore we're going to have an infinite expansion. Clearly, 2/3 is not a positive integer. It's positive, but it's a fraction. And therefore we have an infinite expansion denoted by the plus ... at the end of the series. So now let's tidy up our series. And tidying up some more. Gives us the first 4 terms in the binomial expansion of 1 minus x, all raised to the power 2/3. Now let's find where this expansion is valid. In the expansion of 1 plus bx, all raised to the power n, the expression is going to be valid when mod bx is less than 1. So in our example, bx equals minus x, and therefore mod minus x must be less than 1 in order for the expansion to be valid. And if we want to have a neater expression for mod minus x less than 1, we can rewrite that as mod x less than 1. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at example 3a first. We are required to write down the first 4 terms in the binomial expansion of 1 over 1 plus 3x, all raised to the power 4. We're going to begin by writing this in index form. So we have that this expression equals 1 plus 3x, all raised to the minus 4. We are now going to replace n and x by the relevant value or variable in the expansion of 1 plus x to the power n, or whatever we have in our example which is equivalent. So begin by replacing n by minus 4, since n equals minus 4. So we replace it here, here, and here. And we replace x by 3x, since we're required to expand 1 plus 3x to the minus 4. So we replace it here, here, and here, as shown. Notice again that if n is not a positive integer, no coefficient will be equal to 0, and this will give us an infinite expansion. So of course our value of n is equal to minus 4. Therefore, we have an infinite expansion denoted by the 3 dots at the end of the series. So now we can tidy up. And tidying up some more. Gives us the first 4 terms in the binomial expansion of 1 over 1 plus 3x to the power 4. We're going to now look at where this expansion is valid. In our expansion of 1 plus bx to the power n, we need to have mod bx less than 1. So for our example, the expansion is going to be valid when mod 3x is less than 1. In other words, when mod x is less than a third. Now let's take a look at part B. We are required to use our solution to part A to find the x squared term in the series expansion of 2 plus x all over 1 plus 3x to the power 4. So let's solve this. From part A, we know that 1 over 1 plus 3x all raised to the power 4 is equal to 1 minus 12x plus 90x squared minus 540x cubed and so on. And therefore, if we plug this in to 2 plus x over 1 plus 3x to the power 4, we have this expression here. Now there are 2 ways of making the x squared term. Either we multiply the constant in the first set of brackets by the x squared term in the second set of brackets, or we multiply the x term in the first set of brackets by the x term in the second set of brackets. Therefore, we have that the x squared term is 2 times 90x squared, as shown, plus x times minus 12x, as shown. Giving us 168x squared. Therefore, the coefficient of x squared in the expansion is 168. And now for part C, we are required to state the range of values of x for which the expansion is valid. The expansion is going to be valid when the second set of brackets is valid, because the first set is straightforward, so 2 plus x is valid for all x. However, 1 plus 3x to the minus 4 is only valid when mod 3x is less than 1. In other words, when mod x is less than a third. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We're going to begin by writing the expression in index form. Root 1 minus 3x can be rewritten as 1 minus 3x all raised to the power 1/2. We can now expand this expression by using the highlighted formula. We're going to replace n by 1/2 because n equals 1/2. We're going to replace that here, here, and here. And we're going to replace x by -3x. And we're going to replace that here, here, and here. Now, since n is not a positive integer, we have n equals 1/2, so therefore n is a fraction. No coefficient will be equal to 0 in this expansion, and therefore we're going to have an infinite expansion. And now we can start to tidy up our expression. Giving us the first 4 terms in the expansion of root 1 minus 3x. The expansion of 1 plus bx all raised to the power of n is going to be valid when mod bx is less than 1. So in our example, the expansion is valid if mod minus 3x is less than 1. This can be rewritten as mod x is less than 1/3. And now for part B. By substituting in x equals 0.04 in our series expansion, find a decimal approximation to root 22. From part A, we have this series expansion for root 1 minus 3x, as highlighted on your screen. If we substitute x equals 0.04, we obtain this expression here, or this estimation here, for root 1 minus 3 times 0.04. Tidying up gives us root 0.88 is approximately equal to, because remember we're taking the first 4 terms only, 1 minus 0.06 minus 0.0018 minus 0.000108. Giving us that root 0.88, or 88 over 100, is approximately equal to 0.938092. We can re-express this as shown. Notice that we now have 4 times 22 in the numerator, and this is how we can start to find an estimate for root 22. Root 4 over 100 is equal to 2 over 10, and of course root 22 can be left as shown. And of course the right-hand side remains as it is. giving us that root 22 is approximately equal to 4.69046. And now for another example. Pause the video and have a go. Press play when you're ready to view the solutions. So in part A, in the expansion of 1 plus kx all raised to the minus 3, the coefficient of x is 24. We are required to write down the value of k. So let's solve this. First write 1 plus kx to the minus 3 in index form. As it's already in this format, we don't need to do anything. We can now expand by using our formula. We're going to begin by replacing n by minus 3, since n equals minus 3. And so we're going to replace that here and here. We're also going to replace x by kx, since we're raising 1 plus kx to the power minus 3. So we replace that here and here. Now, since n is not a positive integer, it's equal to minus 3, we have that no coefficient is going to be equal to 0, and this is why our infinite expansion is valid. We can now tidy up our expression. Since the coefficient of x is 24, we have that minus 3k is 24. Implying that k is equal to minus 8. Now let's solve part B. We are required to find the coefficient of the x squared term. From part A, we have this expression for 1 plus kx to the power minus 3. We also have that k is equal to minus 8. And therefore, we have that the coefficient of x squared is 6k squared. Plugging in the value of k, which we obtained from part A, we have that 6k squared equals 6 times minus 8 squared. Which is equal to 384. Therefore, the coefficient of x squared is 384. This brings us to the end of this session. If you have understood its contents, you should be able to expand 1 plus x raised to the power n for negative and rational values of n. You should also be able to specify the range of values of x for which the expansion of 1 plus x to the power n is valid. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.